Consider the moon, our constant companion, a familiar silver coin in the night's velvet purse, the destination of pioneers and the subject of poets. It feels close, a neighbor in the celestial suburb. We can discern its craters with a modest telescope, watch its phases with our naked eyes, and feel its gravitational tug in the rhythm of our tides. It is the only other world upon which human feet have trodden. This proximity is an illusion, a trick of scale and familiarity. The space between our world and the moon spans 384,000 kilometers. To comprehend this, imagine lining up 30 Earths, each one a sphere of swirling blue and white, side by side, touching a planetary necklace stretching across the abyss. That entire chain would fit within the gulf, separating us from our nearest celestial neighbor. If you were to embark on a journey across that void in an automobile, traveling at a steady highway speed of 100 kilometers per hour, never stopping for rest or fuel, you would drive for 5 months before your wheels, metaphorically speaking, touched lunar dust. And light itself, the swiftest messenger in the cosmos, traveling at 299,792 kilometers per second, requires more than a full second to make that leap. 1¼ seconds for a beam of light to traverse what we casually call close. This is what nears means when we measure with the ruler of the universe. It is a redefinition of intimacy, a sobering recalibration of distance, and everything beyond this, every step we take outward from our pale blue dot, only amplifies this extreme, this breathtaking, silent vastness that cradles our existence. Before we venture deeper into the true, the authentic scale of reality, a scale that defies human intuition and stretches the fabric of imagination to its breaking point, we must first understand the messenger, the only constant in this expanding darkness, light. Light travels at 299,792,458 meters per second in the vacuum of space. This is not merely a speed, it is a cosmic constant, a fundamental pillar upon which the laws of physics are built. It is the ultimate speed limit of causality, the rate at which information, influence, and reality itself can propagate through the canvas of space-time. At this velocity, light can circumnavigate the equator of our planet, a journey of 40,000 kilometers, 7.5 times within the span of a single human heartbeat. In the time it takes for blood to surge from a ventricle and return, a photon could race around the world's waist nearly 8 times. Consider the distances you will traverse in a lifetime of driving, tens of thousands, perhaps hundreds of thousands of kilometers. A single, elementary particle of light covers more ground in one fleeting second than you will in all your journeys combined. This is the frenetic, unimaginable pace of light's dance across the emptiness. And yet, this astounding speed reveals its own insufficiency when faced with the true dimensions of our solar home. Our sun, the source of all warmth and light for our world, hangs 149,600,000 kilometers away. A beam of light, unleashed from its fiery surface, must race for 8 minutes and 20 seconds before it finally caresses the leaves of an earthbound tree, or warms the skin of a human face. This creates a fundamental and profoundly strange condition of our existence. We never ever observe the sun as it currently exists. Every sunrise ever witnessed, every sunset ever painted, every photograph of our star is a historical document. We see the sun not as it is, but as it was 8 minutes and 20 seconds in the past. Every human being who has ever drawn breath, from the first hominid to look up in wonder to the modern astronomer peering through a filtered lens, has only ever seen the sun's past. This is not a philosophical abstraction. It is a physical, inescapable fact. If some celestial catastrophe were to occur at this precise instant, if our star were to violently explode into nothingness, we on Earth would remain blissfully, tragically unaware for 8 more minutes. We would continue to see its light, to feel its warmth on our skin, to rely on its gravitational embrace. We would be watching a corpse shine, living in the illuminated aftermath of an event that had already erased our star from existence. The past is not just behind us in memory. It is literally above us in the sky. But here, at this juncture of cosmic delay, is where the narrative deepens, where the simple 8-minute lag becomes a gateway into a far more ancient mystery. That specific photon landing on your retina at this very moment, the one that allows you to see this sentence, did not begin its journey a mere 8 minutes ago. Its origin story is far more epic, more deeply buried in time. It began its struggle for freedom approximately 100,000 years ago, born in the unimaginable crucible of the sun's core. The sun's core is a place of almost inconceivable violence and density, operating at a temperature of 15 million degrees Celsius. Under pressures 250 billion times that of Earth's atmosphere at sea level, hydrogen nuclei are slammed together with such titanic force that they overcome their natural electromagnetic repulsion, the force that makes like charges repel. In this maelstrom, they fuse into helium. This process, nuclear fusion, is the sun's engine, the source of all its energy. Each fusion event releases a burst of energy in the form of gamma-ray photons, the most energetic form of light. But the sun is not a vacuum. Its core is immensely dense, about 150 grams per cubic centimeter, 150 times denser than liquid water. A photon born in this inferno cannot simply zip outward toward space. It is immediately absorbed by a nearby atom, a particle of the solar plasma. That atom, now energized, re-emits the photon a tiny fraction of a second later, but in a random direction. The photon travels perhaps a centimeter before being absorbed again, then re-emitted again and again in a drunken, staggering random walk. It is not racing toward freedom. It is diffusing, bouncing, trapped in a celestial pinball machine of staggering proportions. Physicists at the Lawrence Livermore National Laboratory, using sophisticated computer simulations in 2003 to model this photon's random walk through the radiative zone of the sun, calculated that on average, a photon takes between 10,000 and 170,000 years to travel from the sun's core to its visible surface, the photosphere. The straight-line distance for this journey is just 696,000 kilometers. At light speed in a vacuum, that trip should take approximately 2.3 seconds. Instead, it takes upwards of 100 millennia because the sun, that symbol of clarity and openness, is for light in its interior, profoundly, almost perfectly opaque. It is a prison of light, a labyrinth of plasma. Then, finally, after an epochal journey through the sun's body, the photon breaks free from the photosphere. It escapes into the vacuum of interplanetary space, and here, unencumbered, it finally sprints. It covers the 150 million kilometers to Earth in a clean, straight shot, lasting the 8 minutes and 20 seconds we are familiar with. It lands On your skin, the warmth you feel from sunshine is not minutes old, but ancient. That photon began its escape attempt when Neanderthals still walked the forests and tundras of Europe, when woolly mammoths, creatures of shaggy grandeur, roamed the vast steppes, when the Earth itself was in the clutches of an ice age, with glaciers kilometers thick grinding their way across continents. The sunlight that gilds a blade of grass today is a relic from a world before agriculture, before the pyramids of Giza cast their shadows, before the first symbols were scratched onto clay tablets in Mesopotamia, before our own species, Homo sapiens, had fully crafted its place upon the planet. We are warmed by light from a forgotten age. Now take this profound strangeness, the disconnection between event and perception, the immense hidden histories carried by light, and multiply it across the entire universe. The scale of the cosmos ensures that this is not a peculiarity of our sun, but the universal condition of observation. The nearest star beyond our solar system is Proxima Centauri, a faint red dwarf that is part of the Alpha Centauri triple star system. It lies 4.24 light-years away. A light-year is the distance light travels in 1 year, approximately 9,460,000,000,000 kilometers. Therefore, 4.24 light-years equals roughly 40 trillion kilometers. To grasp this, imagine embarking on a journey at a constant speed of 100 kilometers per hour, driving non-stop day and night for 48 million years. You would have been driving since before the ancestors of modern apes diverged from the ancestors of old world monkeys. When you finally arrived, epochs of geological time would have passed on Earth. And yet, for light, this immense gulf requires only 4 years, 2 months and 27 days to cross. When you observe Proxima Centauri through a telescope tonight, you are not seeing it as it is now. You are seeing it as it existed 4 years, 2 months and 27 days ago. You are watching your own past. You are seeing that star as it appeared when you were 4 years younger. The starlight in your eye is a message from a younger you. This principle escalates with every additional light year. Sirius, the brightest star in our night sky, the Diamond Dog, sits 8.6 light-years distant. Its brilliant, piercing light left that massive, white-hot star 8.6 years in the past. Vega, the jewel of the lyre, is 25 light-years away. The light you see from Vega tonight departed that star around the year 1999 at the turn of the last millennium. Arcturus, the golden-orange guardian of the northern sky, is 37 light-years distant. You are seeing it as it was in 1987. Then consider Betelgeuse, the volatile red supergiant that marks the shoulder of the constellation Orion. It resides approximately 548 light-years away. The light entering your eye from Betelgeuse tonight began its journey in the year 1476. That photon left its photosphere before Christopher Columbus set sail for what he believed would be Asia, before the printing press, invented by Johannes Gutenberg, had fully spread its revolutionary power across Europe, before the Protestant Reformation reshaped the religious and political landscape of a continent. And Betelgeuse, we now know, is a star in its dying throes. Astronomers discovered in 2019 that Betelgeuse has been undergoing significant, mysterious dimming, behavior consistent with a star on the verge of a cataclysmic supernova explosion. If Betelgeuse exploded yesterday, we would not know for 548 years. The explosion could have already happened. The blast wave, a sphere of radiation and ejected matter, could be racing through the interstellar medium toward us at this very moment. But the light, the first herald of that catastrophe, has not reached us yet. When it does, Betelgeuse will suddenly become brighter than the full moon, visible in broad daylight for weeks or months before fading into obscurity. People will look up and say, "Betelgeuse just exploded." They will be wrong. Betelgeuse exploded 548 years before they saw it. We are merely receiving the news, an astronomical telegram from the Renaissance. Polaris, the North Star, our celestial guidepost for millennia, sits 433 light-years away. When you locate Polaris in the sky tonight, you are gazing at light emitted in the year 1591. William Shakespeare had not yet written Hamlet. Galileo Galilei had not yet built his revolutionary telescope. Isaac Newton would not be born for another 52 years. The star we use to navigate, to find our bearing, is a beacon from the age of exploration. Its light a fossil from the dawn of modern science. Every pinprick of light in the night sky is a time capsule, a broadcaster of history written in photons. The farther the star, the older the news, the deeper we peer into the cosmic past. This scaling continues beyond individual stars to the grand structures they inhabit. The center of our galaxy, the Milky Way's dense, enigmatic core, lies 26,000 light-years away. The light we detect from that region, often obscured by great clouds of interstellar dust, shows it as it existed 26,000 years ago. This was during the peak of the last glacial maximum, when ice sheets, kilometers thick, covered much of North America and Europe. Humans were hunter-gatherers, their lives a struggle against the cold, their artistry expressed in magnificent cave paintings in Lascaux and Altamira. The galactic center we see is a snapshot from an age when human civilization was a distant, unimagined future. Our nearest large galactic neighbor, the magnificent Andromeda Galaxy, a spiral of 1 trillion stars, is 2.5 million light-years distant. The soft, fuzzy light you can barely see with the naked eye from a dark sky departed that galaxy 2.5 million years ago. This was the Pliocene epoch on Earth. Australopithecus afarensis, the species to which the famous Lucy belonged, walked the plains of Africa. Our own genus Homo did not yet exist. The climate was warmer and the great jungles of Africa stretched far beyond their current boundaries. We are seeing Andromeda as it was when the very idea of a human was not even a biological whisper. And we are just beginning to scrape the depths of time. The most distant galaxy confirmed, as of recent observations, designated HD1 and discovered in 2022 using data from the Hubble Space Telescope and other observatories, lies an astounding 13.5 billion light-years away. The light we detect from HD1 began its journey when the universe was only about 300 million years old, a mere 2% of its current age. We are observing HD1 as it appeared just after the cosmic dawn, when the first stars and galaxies were igniting in the darkness, when the universe was a fledgling filled with tiny chaotic proto-galaxies. We are looking at HD1's baby pictures, its infant portrait. We have no idea what HD1 looks like now. It has had 13.5 billion years to evolve, to merge with other galaxies, to form stars and die, to be shaped by cosmic forces. The light showing its present state will not reach us for another 13.5 billion years, a span of time nearly equal to the entire current age of the universe. By then, our own galaxy will have merged with Andromeda, our sun will have died, and the fate of Earth will be sealed. We see only the ancient echo. This reveals the first fundamental truth of cosmic scale, a truth that rewrites our understanding of reality. Distance equals time. The vast gulfs of space are not merely empty intervals, they are temporal rivers. To look far away is to look far back. The finite, if immense, speed of light ensures that observation is always an archaeological dig. Space and time are not separate arenas. They are woven together into a single fabric, space-time, as Einstein's theory of relativity established. The universe, in its very architecture, is a time machine. The machine's mechanism is the speed of light, and its fuel is the immense, growing chasms between celestial objects. We are time travelers, peering backward along the light cones of history simply by looking up. But those chasms, those voids between points of light, are about to expand in our minds to levels that defy not just experience, but coherent thought. To understand this, we must first complete a journey through our own solar backyard, realizing that the familiar planets are but the innermost rooms of a mansion whose halls stretch almost to infinity. Neptune, the azure ice giant, orbits 4.5 billion kilometers from the Sun, 30 times Earth's distance. Sunlight, racing outward, requires over 4 hours to reach Neptune's frigid supersonic winds. The Voyager 2 spacecraft, launched in 1977, took 12 years to reach Neptune, arriving in 1989 after a meticulously planned journey that used the gravity of Jupiter, Saturn, and Uranus as slingshots to accelerate it. Without these gravitational assists, the trip would have consumed decades more. Yet Neptune does not mark the frontier of our solar system, not even remotely. Beyond the orbit of Neptune lies the Kuiper Belt, a disc-shaped region of icy bodies, remnants from the solar system's formation. It extends from about 30 astronomical units, where Neptune orbits, to roughly 50 astronomical units from the Sun. An astronomical unit is the average Earth-Sun distance, about 150 million kilometers. Pluto, once considered the 9th planet, is a resident of this belt, taking 248 Earth years to complete a single elongated orbit around our star. The short-period comets, those that return to our skies every few decades or centuries, like Halley's Comet, originate here, occasionally knocked inward by gravitational nudges. Beyond the Kuiper Belt stretches the scattered disk, a sparser population of icy bodies on highly elliptical and inclined orbits, reaching out perhaps 100 astronomical units. And far, far beyond even this lies the theoretical, almost mythical Oort cloud. The Oort cloud is believed to be a spherical shell of trillions of icy planetesimals surrounding our entire solar system. No astronomer has ever directly observed an object in the Oort cloud. It is too distant, too dark, its constituent bodies too small and too widely separated. But we infer its existence from the behavior of long-period comets. These comets, like Hale-Bopp or Hyakutake, which take thousands or even millions of years to complete a single orbit, arrive from all directions in the sky, not just from the plane of the solar system. Their orbital paths suggest they originated in a vast spherical reservoir, a gravitational holding cell at the very edge of the Sun's dominion. The inner edge of the Oort cloud is thought to begin around 2,000 astronomical units from the Sun. Its outer edge may extend to between 100,000 and 200,000 astronomical units, possibly as far as 3.2 light-years from the Sun. That is 75% of the distance to Proxima Centauri, our nearest stellar neighbor. Contemplate this: the Sun's gravitational influence, tenuous but real, reaches almost halfway to the next star. Our solar system is not the compact, tidy arrangement of 8 planets often depicted. It is a vast, diffuse sphere, approximately 3 light-years in diameter, containing trillions of frozen primordial bodies, most of which take millions of years to complete a single ponderous orbit. An object at the Oort cloud's outer boundary, orbiting at a distance of 3 light-years, would have an orbital period of approximately 30 million years. The last time such an object was in its current position, our species, Homo sapiens, did not exist. Our genus, Homo, had just begun to evolve in Africa. Our ancestors were primitive hominins, learning to craft the first crude stone tools, sharing a landscape with saber-toothed cats and giant hyenas. When that distant ice ball completes its current orbit and returns to this same point 30 million years in the future, humanity, in any form we would recognize, will almost certainly be extinct, or evolved into something utterly beyond our imagination. Continents will have drifted into new configurations, the map of Earth rendered unfamiliar. The night sky will display different constellations as the slow proper motion of nearby stars rearranges the celestial patterns. This 3 light-year sphere of frozen debris, barely held by the Sun's weakening gravity, is our true neighborhood, our solar estate. And between our neighborhood and the next, between the outer fringe of the Oort cloud and the Proxima Centauri system, stretches approximately 1.2 light-years of near-perfect nothingness. 1.2 light-years equals about 11,350 billion kilometers of pure vacuum. No planets, no asteroids, no comets, no dust, no gas clouds. Perhaps a stray hydrogen atom per cubic centimeter, perhaps the occasional lonely molecule. This void is the interstellar medium in our local region, a desert of staggering proportion. This gap is typical for our spiral arm of the galaxy, the Orion Cygnus arm. The average separation between stars here is about 5 light-years. 5 light-years of emptiness between island universes of light and warmth. Of course, nature provides exceptions that prove the rule of emptiness. In the Trapezium cluster, a young star-forming region embedded within the magnificent Orion Nebula, 1,344 light-years away, thousands of brilliant, hot, newborn stars are packed into a region just a few light-years across. These stars are infants, only a few 100,000 years old, still swaddled in the glowing gas from which they formed. They haven't had time to drift apart, to feel the galactic tides that will eventually disperse them. In a few million years, this tight-knit family will dissolve, its members scattering into the galactic field. Even more extreme are globular clusters, ancient spherical swarms that orbit the galactic halo. Omega Centauri, the largest globular cluster orbiting the Milky Way, contains approximately 10 million stars crammed into a sphere only 230 light-years in diameter. At the cluster's dense core, stars may average a mere 0.1 light-years apart, about 30 trillion kilometers, roughly the distance from our Sun to the inner Oort cloud. If Earth orbited a star in the core of Omega Centauri, the night sky would be a breathtaking, ceaseless spectacle. Thousands of stars would shine brighter than Sirius does in our sky. Some would be as bright as the full moon, casting sharp shadows, making true darkness an impossibility. The sky would be a permanent, star-studded daylight. But Omega Centauri is a relic, a fossil from the universe's violent youth, when star formation occurred in frenzied bursts. It is the exception that illuminates the rule. The rule is emptiness, profound and pervasive. Our galaxy, the Milky Way, contains between 200 billion and 400 billion stars scattered across a disk 100,000 light-years in diameter. This number sounds impossibly crowded until you perform the calculation of density. If you were to scale down the Milky Way so that Earth's orbit around the Sun, a diameter of about 300 million kilometers, was shrunk to the size of a small coin, just 1 millimeter across, the average distance between stars in our galactic neighborhood would still be about 30 meters. 30 meters of empty vacuum separating millimeter-wide solar systems. Even in our cosmic city, this vast metropolis of hundreds of billions of suns, we are profoundly alone, isolated by gulfs so vast that even light requires years to traverse from one island to the next. The silence between the stars is not just an absence of sound, it is an absence of anything at all. The Milky Way is a barred spiral galaxy. It possesses a central bar-shaped structure composed of densely packed older stars with majestic spiral arms, streamers of stars, gas and dust curving outward from the ends of this bar. We know this not from some external photograph. We are embedded within the disk about 26,000 light-years from the center, but from painstaking, century-long work of cosmic cartography. This effort has been revolutionized in the last decade by the European Space Agency's Gaia satellite. Launched in 2013, Gaia is an astrometric mission of unparalleled precision. It measures the positions, distances, and motions of stars using the principle of parallax, observing how nearby stars appear to shift subtly against the background of more distant stars as Earth orbits the Sun. By 2022, Gaia had catalogued over 1.8 billion stars with exquisite accuracy. This is less than 1% of the galaxy's estimated stellar population, but it is enough to construct a three-dimensional dynamic map of our galactic home in unprecedented detail, revealing its structure, its history, and its future. Our galaxy rotates, but not as a solid disk like a spinning DVD. It exhibits differential rotation, stars closer to the galactic center orbit much faster than those farther out. Our Sun, located in the galactic suburbs, orbits at about 220 kilometers per second, nearly 800,000 kilometers per hour. Even at this blistering speed, it takes the Sun approximately 225 to 250 million years to complete one full circuit around the galactic center. Astronomers call this span a galactic year or a cosmic year. The last time our Sun was at this precise point in its galactic orbit, Earth was undergoing the Permian-Triassic extinction event, the most severe mass extinction in the planet's history. Roughly 96% of marine species and 70% of terrestrial vertebrate species vanished. The causes are still debated: catastrophic volcanic eruptions in the Siberian traps, a possible asteroid impact, a deadly combination of factors, but the result was a near-complete reset of life's complexity. Dinosaurs did not yet exist. Mammals did not yet exist. Flowering plants were a distant future innovation. The supercontinent Pangaea was assembled, containing almost all of Earth's landmass in one monolithic entity. 1 galactic year from now, 250 million years in the future, Earth will be utterly unrecognizable. Plate tectonics will have rearranged the continents into a new supercontinent, often dubbed Pangaea Ultima. The Sun will be about 5% brighter, altering Earth's climate profoundly. Ocean chemistry will have changed. Whatever species dominate the planet, they will not be human. Homo sapiens will be as ancient and extinct as the trilobites are to us now, a faint fossil layer in deep time. Our orbit is not a simple flat circle. As we travel around the galactic center, the Sun and all the stars in the disk oscillate up and down through the galactic plane, following a wave-like path. We bob above the plane, then sink below it, then rise again with a period of roughly 70 million years. Currently, we are about 70 light-years above the plane, moving upward at 7 kilometers per second. In about 30 million years, we will reach our maximum height, perhaps 250 light-years above the plane, before gravity pulls us back down through the plane and below it only to rise once more. Some scientists have proposed a controversial hypothesis that these vertical passages through the denser, dustier galactic plane might correlate with periods of increased comet impacts on Earth, perhaps triggering mass extinctions. The evidence is suggestive but not conclusive. What is certain is this slow cosmic bobbing, a gentle undulation on a scale of tens of millions of years. A reminder that our motion is complex, woven into the grand gravitational tapestry of the galaxy. At the heart of this tapestry, 26,000 light-years away, hidden behind vast opaque clouds of interstellar dust that block visible light, sits Sagittarius A, the supermassive black hole at the center of our galaxy. It contains approximately 4.1 million times the mass of our Sun. 4.1 million solar masses compressed into a region with a diameter roughly 17 times that of the Sun, about 25 million kilometers across, smaller than Mercury's orbit. How can we be so certain this invisible object is a black hole? Because for 27 years, from 1992 to 2019, astronomers, primarily at the Max Planck Institute for Extraterrestrial Physics in Germany, tracked individual stars orbiting this nothingness with exquisite precision. Using powerful instruments like the Very Large Telescope in Chile and the Keck Observatory in Hawaii, they mapped the paths of stars hurtling around the galactic center. One star, designated S2, follows a highly elliptical 16-year orbit. At its closest approach, or periapsis, S2 comes within a mere 1,400 astronomical units of Sagittarius A, screaming through space at a velocity of 7,650 kilometers per second, over 2.5% of the speed of light. By meticulously tracking S2's orbit, astronomers detected the subtle fingerprints of Einstein's general relativity, the gravitational redshift, where light from the star loses energy as it climbs out of the black hole's deep gravitational well, and the precession of its orbit, where the ellipse itself rotates over time. The measurements matched the predictions of general relativity with stunning accuracy, confirming not only the theory, but also the existence of a 4 million solar mass object confined to a volume so small that only a black hole could explain it. In May 2022, the Event Horizon Telescope Collaboration, a global network of radio telescopes acting as one Earth-sized instrument, released the first direct image of Sagittarius A's immediate environment. The image shows a distinctive ring of bright, Doppler-shifted gas orbiting at relativistic speeds, with a dark, central shadow. That shadow is the event horizon's silhouette, the point of no return. The event horizon for Sagittarius A is about 24 million kilometers in diameter. Once any object, a star, a gas cloud, a photon, crosses this boundary, escape becomes not merely difficult but geometrically impossible. Within the event horizon, the curvature of space-time is so severe that all paths, every possible direction, lead inexorably inward toward the singularity at the center. The singularity is where general relativity predicts infinite density and infinite curvature, a point where the known laws of physics break down completely. We do not know what truly occurs at a singularity. Understanding it requires a theory of quantum gravity that unites the macroscopic world of relativity with the microscopic world of quantum mechanics. A quest that continues to occupy the greatest minds in physics. Sagittarius A* is currently quiescent, dormant. It is not actively consuming large amounts of matter. Occasionally, a passing gas cloud or an unfortunate star is torn apart by its tidal forces, producing a brief flare of X-rays, but mostly it sits in silence, a sleeping leviathan at the heart of our city of stars. This quietude is common for supermassive black holes in the present-day universe. But in the cosmic past, roughly 10 to 13 billion years ago, the cores of most galaxies were violently active. These active galactic nuclei, or quasars, shone with ferocious brilliance as matter cascaded into their central black holes at phenomenal rates. The brightest known quasar, SDSSJ 0100 plus 2802, discovered in 2015, has a luminosity 420 trillion times that of our Sun. It is powered by a black hole of about 12 billion solar masses, consuming matter at the theoretical maximum rate. This quasar is 12.8 billion light-years away. We see it as it was when the universe was only 900 million years old. The existence of such a monster black hole so early in cosmic history presents a profound puzzle for astrophysicists. Black holes grow by accretion and mergers, but both processes take time. How did a black hole accumulate 12 billion solar masses in less than a billion years? Did it form from the direct collapse of immense gas clouds in the early universe? Were the seeds already massive, hundreds of thousands of solar masses? The James Webb Space Telescope, with its infrared eyes peering into this epoch, is now searching for clues to solve this mystery. What we do know is that a supermassive black hole appears to reside at the center of virtually every large galaxy. The Andromeda Galaxy's black hole is estimated at 100 to 200 million solar masses. The giant elliptical galaxy Messier 87, 55 million light-years away, hosts a black hole of 6.5 billion solar masses, the first black hole ever directly imaged by the Event Horizon Telescope in 2019. These black holes are not passive ornaments. They are fundamental actors in galactic evolution. When they feed, the immense energy released in the form of jets and radiation can heat surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, the central black hole acts as a galactic regulator, a thermostat controlling the star formation rate of its entire host galaxy. A remarkable correlation exists. The mass of a galaxy's central supermassive black hole is consistently about 0.1% of the mass of the galaxy's central bulge of stars. This tight relationship suggests that black holes and their galaxies grow together over cosmic time, intertwined in a complex dance of feedback and co-evolution. Our own galaxy's future is one of dramatic change. In approximately 4 billion years, the Milky Way and the Andromeda galaxy will begin a slow, majestic collision. They are currently approaching each other at about 110 kilometers per second. The term collision is misleading for galaxies. It is not a crash of stars. The spaces between stars are so immense that stellar collisions are vanishingly unlikely. Instead, the two galaxies will pass through each other like ghosts, their stars streaming past one another unharmed. But gravity will sculpt chaos. The immense tidal forces will distort both galaxies beyond recognition, pulling out long, luminous tails of stars and gas stretching hundreds of thousands of light-years into intergalactic space. The collision and compression of vast gas clouds will trigger a fireworks display of star formation, birthing millions of new stars in a brilliant starburst. Over 1 billion years, the two galaxies will separate, then fall back together, eventually merging over a total timescale of about 2 billion years. The two supermassive black holes at their centers will spiral inward, emitting gravitational waves before finally merging into a single, more massive black hole. The end product will be a large elliptical galaxy, already named Milkdromeda or Milkomeda by astronomers. Sophisticated computer simulations, such as those run by astrophysicists at the Harvard-Smithsonian Center for Astrophysics, suggest our solar system will likely be flung to a wider orbit but will survive the merger intact. If any civilization is present on Earth 4 billion years from now, a monumental if, given that Homo sapiens has existed for only 300,000 years, they would witness a sky of unimaginable splendor filled with newborn stars and the luminous wreckage of two galaxies intertwining. But humanity will almost certainly not be here to see it. Long before this merger, in about 1 billion years, the Sun's steadily increasing luminosity, a natural consequence of its aging process as it fuses hydrogen into helium, will have increased by roughly 10%. This will be enough to trigger a runaway greenhouse effect on Earth, evaporating the oceans and transforming our planet into a scorching hellscape akin to Venus, with surface temperatures hot enough to melt lead. All complex life will have ended. In 5 billion years, the Sun will exhaust the hydrogen in its core, swell into a red giant, likely engulfing Mercury and Venus and rendering Earth a charred, lifeless cinder. Eventually, it will shed its outer layers into a beautiful planetary nebula, leaving behind a cooling white dwarf, an Earth-sized ember containing half its original mass. This is the fate of all stars like our Sun, a fate being played out with countless stars across the Milky Way at this very moment. We are living in what cosmologists call the stelliferous era, the age of stars. It is a finite epoch. The Milky Way currently forms about 1.5 new stars per year, but this rate is declining. In the early universe, galaxies produced stars 10 to 100 times more vigorously. The raw material, hydrogen gas, is being consumed, locked away in long-lived stars, or blown out of galaxies by stellar winds and supernovae. In perhaps 10 trillion years, star formation in our galaxy will effectively cease. The last new stars, small frugal red dwarfs, will ignite. The smallest red dwarfs can shine for 10 trillion years themselves. But when the last of these finally winks out, the stelliferous era will end. The universe will enter the degenerate era, populated only by the corpses of stars. White dwarfs, neutron stars, and black holes slowly cooling and dissolving over timescales that make billions of years seem like an eye blink. And yet, even within this awe-inspiring narrative of a single galaxy, we have only explored our local island. The universe contains not 1 but 2 trillion such islands within the observable volume alone. 2 trillion galaxies, each with hundreds of billions of stars scattered across 93 billion light-years of space. But they are not scattered randomly. They are arranged in a vast cosmic web, the largest structure in existence, a froth of galaxies surrounding unimaginable voids. Let us build this structure from the ground up. Our Milky Way is part of the local group, a gravitationally bound collection of about 80 galaxies within a diameter of 10 million light-years. The dominant members are the Milky Way, Andromeda, and the Triangulum galaxy, a smaller spiral. The rest are dwarf galaxies, small satellites orbiting the larger ones. The large and small Magellanic Clouds, visible from the southern hemisphere, are such dwarf galaxies slowly being gravitationally shredded and absorbed by the Milky Way, a process of galactic cannibalism that has occurred many times in our galaxy's past. The local group itself is but a speck within the Virgo supercluster, a massive filament of galaxy groups and clusters spanning 110 million light-years and containing at least 100,000 large galaxies. At the heart of this supercluster lies the Virgo cluster, a dense knot of about 1,500 galaxies. But in 2014, astronomers mapping the peculiar motions of galaxies discovered that the Virgo supercluster is merely an appendage of an even vaster structure. They named it Laniakea, Hawaiian for immeasurable heaven. Laniakea is a supercluster complex, a gravitational watershed spanning 520 million light-years and containing approximately 100,000 large galaxies. Our entire local group is flowing along filamentary pathways within Laniakea toward a gravitational focal point known as the Great Attractor, a region of immense mass hidden behind the dusty plain of our own Milky Way. The Great Attractor itself is being pulled toward the even more massive Shapley supercluster, over 650 million light-years away. This is the cosmic web, a hierarchy of structures, from groups to clusters to superclusters to filaments, all drawn together by gravity, forming a delicate, lace-like pattern across the cosmos. And between these bright filaments lie the voids, vast spherical regions of space almost completely devoid of galaxies. The Boötes void, discovered in 1981, is 330 million light-years across. In a volume of space where one would expect 10,000 galaxies, it contains only about 60. If you found yourself at the center of the Boötes void, you would see nothing in any direction with even the most powerful telescope. No galaxies, no stars, just perfect, unbroken blackness, punctuated only by the uniform glow of the cosmic microwave background. We ourselves may reside in a local void, the KBC void, which spans 2 billion light-years. This possible underdensity might even influence our measurements of the universe's expansion rate, leading to current tensions in cosmology. How did this magnificent, frothy structure arise? The seeds were planted in the first infinitesimal fraction of a second after the Big Bang. During a period called cosmic inflation, the universe expanded exponentially, stretching quantum fluctuations, tiny random variations in energy density at subatomic scales, to cosmic proportions. These stretched fluctuations became the slight density variations in the early universe. Over billions of years, gravity acted as an amplifier. Regions slightly denser than average attracted more matter, growing denser still, eventually collapsing into galaxies and clusters. Regions slightly less dense were drained of matter, becoming voids. We have captured a baby picture of these seeds. The cosmic microwave background radiation, the afterglow of the Big Bang, released when the universe was 380,000 years old. Satellite maps of this radiation, most exquisitely from the Planck mission, show temperature variations of 1 part in 100,000, the precise imprints of those quantum fluctuations now writ large across the entire sky. Every galaxy, every star, every planet, and every one of us originated from those microscopic quantum jitters, magnified to a cosmic scale by inflation and shaped by gravity. It is a connection of unimaginable profundity. The largest structures in existence are direct descendants of the smallest events permissible by physics. Yet this majestic visible universe, the stars, galaxies, and cosmic web, comprises only about 5% of the total content of the cosmos. The remaining 95% is dark and mysterious. 27% is dark matter, an invisible form of matter that does not emit, absorb, or reflect light, but whose presence we infer through its gravitational grip on galaxies and clusters. It forms vast, diffuse halos that provide the scaffolding upon which galaxies form. Without dark matter, galaxies as we know them could not exist. Stars would fly apart. The bullet cluster, the aftermath of a collision between two galaxy clusters, provides stunning evidence. The visible gas, slowed by friction, lags behind the majority of the mass, which, revealed by gravitational lensing, marched right through a clear signature of collisionless, invisible dark matter. 68% of the universe is something even more enigmatic: dark energy. This is not matter at all, but a property of space itself that causes the expansion of the universe to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy's nature is perhaps the greatest mystery in modern physics. It acts as a sort of anti-gravity on cosmic scales, pushing space apart. If it is a cosmological constant, as Einstein once postulated and then discarded, its density remains constant as the universe expands, meaning its influence grows dominant over time. Dark energy determines the ultimate fate of everything. For we now arrive at the most mind-bending consequence of scale, woven from the threads of light speed, expansion, and dark energy, the horizon of what we can ever know. The observable universe is a sphere 93 billion light-years in diameter, centered on us. But the universe is only 13.8 billion years old. Why is the observable universe not simply 27.6 billion light-years across? Because space itself has been expanding during the billions of years that the light from the most distant galaxies has been traveling to us. A photon emitted 13 billion years ago from a primordial galaxy was, at the time, much closer to us. But as it traveled, the space between it and us stretched. The photon finally arrives, telling us of a galaxy that is now, due to that relentless expansion, 46 billion light-years away. We see its ancient light, but the object itself is forever beyond our reach. This expansion, driven by dark energy, creates a fundamental limit, a cosmic horizon. For galaxies beyond a certain distance, space is expanding so fast that light they emit today can never reach us. They are permanently beyond our causal reach, their information forever lost. Worse, as expansion accelerates, this horizon is shrinking. Galaxies that are visible today will, one by one, cross this horizon and disappear from the sky of any future observers. In about 150 billion years, all galaxies outside our merged local group will have vanished beyond the horizon, their light redshifted to infinity. Future astronomers in the Milky Way Andromeda merger will see only their own galaxy adrift in an endless, empty blackness. They will have no evidence of the cosmic microwave background, no clue that the universe is expanding, no hint of the Big Bang or the vast cosmos that exists beyond their island. The universe will have hidden its own history. We therefore live in a uniquely privileged era, a cosmic golden hour. We are late enough that the universe has cooled, stars have formed, heavy elements for planets and life have been forged, and consciousness has arisen. But we are also early enough that the universe is still transparent, its history still legible in the light from distant galaxies and the whisper of the microwave background. We exist in a narrow window of cosmic time when the universe is both habitable and knowable. This window will not last forever. Peering further into the future, across timelines that numb the mind, we see the heat death of the universe. After the last red dwarf dies, trillions of years from now, the degenerate era will see the gradual evaporation of galaxies and the decay of protons over timescales of 10 to the power of 40 years. The black hole era will follow, where only black holes remain, slowly evaporating via Hawking radiation over epochs of 10 to the power of 100 years. Finally, in the dark era, the universe will contain only a dilute sea of fundamental particles and radiation approaching absolute zero, with no energy gradients, no structure, no change, eternal stillness. If the entire lifespan of the universe were compressed into a single calendar year, the Big Bang occurs at midnight on January 1st. The first stars form around 12:40 a.m. Our Sun and Earth form around September 2nd. Complex life emerges in mid-December. All of human history, from the first cities to the present day, occurs in the last quarter of a second before midnight on December 31st. The last stars die around 6 a.m. on January 2nd of the following year. The remaining 364 days, and all the years that follow for eternity, are an endless, dark, silent emptiness. We exist in the universe's brief, glorious morning. And you, a conscious assemblage of atoms forged in those ancient stars, are here for this fleeting moment. You are the universe's way of knowing itself. In all that vastness, across 2 trillion galaxies, amid the silent eons of darkness that preceded and will follow the stellar dawn, you are a point of light, of awareness. You are stardust that has coalesced into a form that can contemplate its own origins, trace its lineage back to the first instant, feel awe in the face of the abyss, and find meaning in the connection. The true scale of the universe is not just measured in light years, or billions of years. It is measured in the profound, beautiful, and terrifying contrast between the infinite, unconscious cosmos and the fragile, temporary, precious spark of consciousness that has, against all odds, flickered into being within it. You are that spark. For a little while, the universe is awake, and it is awake in you. Treasure this moment of cosmic awareness. It is the rarest thing in all of existence. Good night.